Welcome to the first talk in the second webinar series presented by the International Adsorption Society. The IAS is an international organization dedicated to advancing adsorption as a solution to scientific, engineering, and human welfare challenges through the promotion of adsorption research and education. We hope that all of our attendees, their families, and their colleagues are safe amid the ongoing COVID-19 pandemic. We thank everyone for attending the webinar today. The webinar series in the spring of 2020 was an immense success, and the recordings of those webinars continue to be viewed on YouTube. Based on that success, the IAS decided to continue holding webinars, though in a slightly different format and sequence. Over the next year, we aim to host one webinar per month. Speakers will include international experts from both industry and academia, as well as PhD students and early career researchers. Subsequent webinars will be announced on the IAS mailing list and the IAS Twitter feed. Today's webinar will be presented by Peter Ravikovitch of the ExxonMobil Research and Engineering Company. I'm Daniel Sidarius of NIST in the United States and the Secretary Treasurer of the IAS. Today's host will be Nick Wilkins, a student at the University of Alberta, and questions to the speaker will be moderated by both Professor Arvind Rajendran, also of the University of Alberta, and myself. We are required to remind attendees and future viewers that the views expressed by the speaker, host, and other moderators are not necessarily those of the IAS or of the institutions associated with those individuals. We ask that you consider joining the IAS as a regular member if you're not already. Our dues are minimal, only $20 US per year, but support the publication of our flagship journal, Adsorption, contribute to travel grants and workshop seed funding for IAS members and affiliated groups, as well as aid the organization of our triennial conference on the fundamentals of adsorption. Members also receive free access to IAS-supported materials, including our journal, as well as the adsorption database published by Springer Materials. Anyone can follow the IAS on Twitter at our handle @intadsos for future updates regarding IAS events, webinars, and information about scientific meetings. Please help expand our YouTube channel by subscribing. At this point, I'm going to hand over the host responsibilities to Nick Wilkins, who will introduce our speaker and then begin our presentation.
All right. I am pleased now to introduce today's speaker, Dr. Peter Ravikovitch. Dr. Ravikovitch is a member of the technical staff and a program leader at the ExxonMobil Corporate Strategic Research Laboratory in Annandale, New Jersey. His experience includes a year as a DAAD fellow at the Johannes Gutenberg University in Mainz, Germany. Prior to joining ExxonMobil, he had worked at TRI Princeton on advancing and commercializing classical density functional theory methods for adsorption characterization of nanoporous materials. After joining ExxonMobil in 2007, he has been involved in a number of projects related to separations. His primary research interests include fundamentals of adsorption in transport zeolites, MOFs, and carbons, spanning both modeling and experiments. He has co-authored more than 70 publications totaling more than 10,000 citations and over 20 patents. He's served on the board of directors at the International Adsorption Society, and currently he is the chair of the Adsorption and Ion Exchange area at the American Institute of Chemical Engineers. During the webinar, questions can be submitted to the speaker through three methods. You can do it if you're on Zoom through the Q&A tab at the bottom of your screen, or you can post a comment on YouTube, and those comments will be forwarded to the Zoom hosts. So questions will be addressed partway through the seminar and also at the end of the seminar. So we'll take a couple at the midpoint, and then we'll do the rest at the end. So with that, I'll ask Peter to share his screen.
Good morning, everyone. Can you hear me well?
We can hear you.
Good morning, everyone, or whatever time you have. First of all, thank you very much, organizers, for inviting me for this webinar series. It's a really privilege to speak here today. Before we start, I would like to start on a little bit of a sad note. And as you know, Klaus Unger passed away a month ago, and I was fortunate enough to work for a year in his lab, and he was a true gentleman and a wonderful scientist, mentor, and we're going to miss him dearly. The topic of my today's webinar is adsorption fundamentals for separations, modeling and experiments. I will try to cover everything in about 1 hour. And to begin with, let me start with the bigger picture before we delve into the details. So I work in ExxonMobil Research and Engineering Corporate Strategic Research. Our labs are in Central New Jersey in the United States. The corporate strategic research, the charter of the corporate research, and the goal is to perform research with high reward, high risk research for the corporation with the goal 10, 15 years ahead, and look on advantage technologies and new science areas for the ExxonMobil Corporation. One of the areas of research which I'm involved in is separations. And separations is a huge area in our chemical and petrochemical industry. If you look on the paper which was presented recently by David Scholl and Ryan Lively, they assessed the importance of chemical separations in the US industrial energy use. And they have estimated that US industrial energy use chemical separation account for 10–15% of the nation's total energy consumption. If you think about this, this is a huge number. The list of separations which are very energy intensive and important is listed on the right. And as you can see, most of these separations are occurring in the petrochemical business. And therefore, it is very important to improve the energy intensity of these separations. So how can we do that? One way of doing this is to use technologies which are less energy intensive compared to conventional separation technologies such as, for example, distillation. Adsorptive and membrane separations is one of these technologies. And so I'm give you a very simple primer on adsorptive membrane separations. In adsorptive membrane separations, we're exploring differences in equilibrium between different molecules. So equilibrium is characterized by adsorption isotherms. And for example, if you look on the difference in equilibrium between high pressure and low pressure loading of a component on an adsorbent, you can explore this difference in the so-called pressure swing adsorption process. Likewise, you can explore the difference in loadings of a molecule on adsorbent by temperature, and in which case you can adsorb at a low temperature, for example, and desorb at a higher temperature, which would be a temperature swing adsorption process. Another important way of separating molecules is by kinetics. And this is something which I am very interested in. In this case, we're exploring the difference in the diffusivities or transport properties of molecules. And in this case, example is, for example, the uptake of one molecule is much faster than uptake than the other molecule. And in this case, you can separate molecules in addition to equilibrium also by kinetics. An extreme example of kinetic separation would be so-called molecular sieving, when one of the molecules is so slow that it effectively does not enter the porous structure or adsorbent. So what do we need to do in order to develop such separations. So of course, you need to have materials which would be able to do that. And also you need to be able to predict fundamental and measure or predict fundamental properties such as equilibrium, adsorption, isotherms, and also diffusional properties of molecules, which will be very much unique to each of the porous material considered. And in this case, we want to use experiments, but we also want to use predictive molecular simulations as much as possible to screen as many materials as possible and predict the properties of these materials at conditions which are difficult to assess experimentally. This is an example of adsorption technology which our company has been developing, and this is so-called rapid cycle adsorption. First of all, on the left, you see from the DOE report the relative energy use of different technologies, and you can see adsorption and membrane separations generally have much lower energy consumption compared to distillation and other technologies which involve the phase changes. And so the rapid cycle adsorption, the advantage of rapid cycle adsorption is that you can perform adsorption cycles much faster, which increases the throughput of your adsorption equipment and allows you to shrink the size of the equipment very substantially. We have experience with this technology starting from hydrogen purification unit, which was working at one of our refineries to purify hydrogen streams. We're currently testing the unit to separate water from natural gas, to dehydrate natural gas. And in the future, this technology, which is called RapAdsorb, can be used for example, for gas treating applications. And which you can see the advantage of this technology because of the rapid cycles, it's a much smaller equipment and therefore much lower cost and other potential advantages. So with that, I would like to go to the topic of my presentation. It will not be on process development, it will be on fundamentals of adsorbents and what goes behind some of these technologies. So the topics will be, I will talk about the separations using small-pore zeolites. So we will cover kinetic separations and briefly touch on experimental techniques used. And we will focus on quantitative predictions of adsorption and diffusion in this type of systems. And I will emphasize the importance to accounting for the framework flexibility of zeolites. Then we will transition to materials which are metal organic frameworks and generally much more flexible materials. So we'll talk about zeolitic and metazoate frameworks. And in addition to flexibility, these materials also have prominent phase transitions, which result often in a step-like isotherms and behavior, which is generally not seen for the zeolitic materials. And the last topic is heats of adsorption. So it goes across regardless of what material you use, and heats of adsorption are extremely important for the understanding and for the design of your process, because that's the energy of adsorption which you need to put back in order to desorb molecules. And then we will conclude and we'll have some suggested readings and acknowledgement. So the plan is to cover the first two topics and then have a short break for questions and then finish with the last topic on heats of adsorption. So let me start on fundamentals of separations using small-pore zeolites. So when we're talking about small-pore zeolites, we talk about materials of this type, and these are some examples of some of these zeolites. They usually have sufficiently large cages where we can adsorb molecules, but these cages are separated by narrow windows. Let me make my pointer laser. So these are windows. For example, this is 8-member ring windows consisting of 8 oxygen atoms. And these windows are pretty narrow, and they can be controlled very well by synthesizing different materials. And what is very interesting is how the diffusivity of molecules changes drastically when the size of the molecules approaches the size of the window. And this is an example how methane or ethylene or propylene diffusion, for example, in a range of different zeolites starts to drastically change as you decrease the window size. So this creates very interesting opportunities for kinetic separations, but at the same time, it also creates fundamental difficulties, because when the size of the molecule becomes comparable to the size of the window, it is a very sensitive system. Therefore, in order to be able to study this model, this system, you need to have very accurate molecular simulations and also accurate experiments. So one of the materials which we've been looking at is the DDR zeolite, for example. This zeolite has a windows of about 3.6 angstrom. And these are examples of these DDR zeolites, very nice crystals of different sizes. And this is example of molecular simulation of, say, methane and carbon dioxide mixture in this structure. And as you can see, windows and cages in these zeolites. It's a hexagonal arrangement of cages, and each of these cages has 3 windows to neighboring cages. So it's effectively 2-dimensional structure in this case. So how can we study the transport of molecules in these zeolites? I'm not going to review and talk about different methods to study diffusion. I would like to point you to the webinar by Stefano Brandani, and also I will have literature in suggested literature for reading. But one of the techniques we've been using is so-called zero-length chromatography, which is a chromatographic technique by which we use a small amount of material and we pack a column, which is essentially a small amount of material. And the essence of zero-length chromatography is that you establish uniform concentration of your molecules, you saturate the material fully, and then you purge the adsorbed gas with something else, say with helium, and you monitoring the effluent concentration, and by applying appropriate mathematical model, you can extract diffusivities. There are different models applicable to do this, and again, for pure crystalline diffusion, or when you have substantial volume of fluid adsorbed versus non-adsorbed, as well as if you have surface barriers. So this is a typical example of methane ZLC curves performed at different flow rate conditions. So you have this typical pattern of parallel curves at different flow rates, and you can extract the diffusion coefficient, which is on the order 10⁻12 meters squared per second. You can cross-check it by using different crystals, and the diffusion times will depend on as a square of the crystal size. So it's a very sensitive method to double check with a different crystal, and we're getting essentially the same diffusivity. And this diffusivity corresponds to intracrystalline diffusivities. Here is some literature where other methods were used to study diffusion in DDR crystals using membrane measurements, using PFG and MR, using infrared microscopy methods, and all of them show results in the same, with about 10⁻12 meters squared per second. So it's a good reference system. Now, how we do molecular simulation? I'm not going to give you a big lecture on molecular simulations. I would like to point out 2 wonderful lectures by Randy Snow and others. In essence, in the classical molecular simulations, we use the force field, which describe molecules as a set of Lennard-Jones centers with charges. And in case of polyatomic molecules, we also have terms related to bending and torsion and bond stretching. As far as simulations, interactions of a molecule with your adsorbent is concerned, again, it's Lennard-Jones interactions with atoms and also Coulombic interactions. What is important to realize that molecular simulations become much easier when you assume that the solid is a rigid framework. Because in this case, you can pre-calculate all the interactions between your Lennard-Jones atoms and the atoms within the solid and create a grid, which saves you hundreds, if not more, times CPU time. So this is especially useful for Monte Carlo simulations of adsorption. So in order to simulate a flexible framework, you will have to have a force field which describes all the flexibility, all the flexibility of the framework, and this generally is not known for many structures, and many structures are unique. And in this case, these force fields are not as well developed as the force field for fluid-fluid interactions. So again, for simulating adsorption isotherms, we use so-called grand canonical Monte Carlo simulations. We use displacement, removal, and addition of molecules. For simulations of diffusion, the methods is the molecular dynamics simulations, where the Newton equations of motions are solved for all the atoms, and then trajectories of the atoms can be used to calculate so-called safe diffusion coefficient according to Einstein relation. Molecular dynamics simulations can be performed with the flexible structure if the force field is available. It is more computationally expensive, but not terribly expensive. The problem, again, is availability of these force fields, but the biggest problem with molecular dynamics is that there is a range of diffusivities and about 10⁻12 meters squared per second. If diffusivities are faster, then molecular dynamics can be used. If diffusivities are slower, then transition state or free energy methods can be used in order to calculate the free energy barrier and then calculate diffusion using transition state theory. As I mentioned before, the quality of the force field is the most important for all the simulations, adsorption or diffusion. And one of the approach we've been taking in collaboration with the group of David Scholl at Georgia Tech is to develop force field based on first principle calculations without resorting to fitting to experimental measurements. And in order to do that, we start with the DFT calculations, where we perform periodic DFT calculations on a periodic cell of a crystalline material and create the energy grid. But DFT is not always accurate, and you need to correct this DFT using much more accurate quantum chemical calculations using coupled cluster methods. And we use it for specific pairs of atoms. And by doing this, we create the energy grid, which then can be fitted to the force field. And the force field will include Coulombic and Lennard-Jones interactions. And then we can use classical Monte Carlo and molecular dynamic simulations to predict adsorption isotherms and diffusivity. So this is the overall approach. And here are some publications over the years we published using this approach, which we applied to zeolites, first to siliceous zeolites, then to selected cationic zeolites, and so on. And I will be showing some of the examples later on in the talk. For example, for siliceous zeolite, this is the ITQ29, which is the all silica LTA structure. This approach works really well for predicting adsorption isotherm. This is an example of methane adsorption isotherms at different temperature in comparison with the experimental measurements. And this is a very good agreement. as well as the agreement for the heats of adsorption, which were measured by calorimetry, and I will be talking more about calorimetry. The point here, there was no fitting involved in these calculations. So these are predictions. What about diffusion? As I mentioned, when the size of the molecule approaches the size of the window through which this molecule diffuses, this system becomes very sensitive. And this is a very good example. Diffusion of methane in a range of these 8-member ring zeolites, LTA, chabazite, and DDR. So these structures, the size of the window changes from 4 to 3.7 to 3.6 angstrom. And diffusivities change for methane, change by about an order of magnitude. So 10 minus 10, 10 minus 11, 10 minus 12. So what is plotted here is predicted by molecular simulations. Diffusivity is predicted by molecular simulations by using different force fields, which were reported in the literature. And most of these force fields were reported that they work pretty well for adsorption, equilibrium adsorption of methane in silica zeolites. But when we apply these force fields to calculate diffusion, the results differ by many orders of magnitude. And when we use the force field, which we developed based on first principle calculations, we actually get results which are very good agreement with experimental measurement. This is a really interesting example showing that for certain properties like diffusion, if the force field is not accurate, the results could be very misleading. Another complication is that zeolites are actually flexible. And if you do calculations, for example, so-called ab initio molecular dynamic calculations, we do not rely on the force field. It's basically, it's a molecular dynamics, but at every step, you calculate your energies and forces using DFT, at DFT level. What you find is that the window, which is nominally crystallographically 3.6 by 4.5, it actually changes all the time. And you can plot the so-called histogram of this minimum window dimension. And you can see that's a pretty broad histogram. And what is interesting, if you put a nominal size of CO2 molecule and nominal size of methane molecules, you can see that flexibility is important for this material. So there is no clear cut that, for example, methane is totally excluded from the structure and CO2 is just diffuses easily without colliding with the window oxygen atoms. So this flexibility needs to be taken into account. How can we do this? So in the literature, there was a suggestion that flexibility can be taken into account by performing simulations with the flexible structure and then taking some sort of average. And it works for some of the structures, such as, for example, LTA, but it doesn't work for other structures, for example, like chabazite. And the problem here is it really depends on the number of directions in this fluctuating window, and also on degree of harmonicity of atomic vibrations. So if the crystal vibrates harmonically, in other words, at all temperatures, it is essentially the same structure, then this effects of flexibility, if you take the average structure, it will be equal to crystallographic rigid structure. However, if the crystal vibrates unharmonically, then the flexibility will change the nominal window dimensions quite more substantially. So that's the difference. Another way of simulating flexibility in zeolites in a more efficient way is to use so-called snapshot method. So in the snapshot method, instead of doing simulations with the flexible structure, what one can do is simulate empty structure and take snapshots and then use these snapshots to perform molecular dynamic simulations with rigid structures and periodically replace the snapshots. And in this case, you decouple the flexibility of the framework from molecular diffusion, but if they can be decoupled in this case, this method is very efficient. And the frequency with which you need to switch these snapshots should correspond to the frequency of vibrations of the window within the window, which is usually a low frequency vibration, which you can calculate by, for example, so-called vibrational density of state. And it basically gives you the frequency with which these windows fluctuate. However, if the molecules are larger, and what can happen is that these molecules, they actually can expand the zeolite or other porous material during diffusion. And this is, you can see it very nicely here. These are simulations performed also in David Scholl's group using so-called transition path sampling. And what is shown here is a methane diffusion in LTA zeolite, which passes quickly through the 8-member ring window, and butane diffusion through 8-member ring zeolite, LTA. As you can see, butane gets stuck in the window for quite some time. And if you look on the window size as a function of simulation time, it actually expands quite substantially. It doesn't happen for methane, but it does happen for butane. So this is very important. So this coupling means that you can no longer expect that a method like a snapshot method I just showed you is going to work, because now you need to take into account the coupling. Perhaps one of the most extreme example of this coupling is the ITQ55 zeolite. And this is the zeolite we've been working in collaboration with the group of Avelina Korma from Valencia. So this zeolite has heart-shaped cages. And at the bottom of this cage, you have two elongated 8-member ring windows. And the nominal size of these windows, the minimal dimension is 2.1 angstrom. This is way smaller than the size of the typical molecules. Nevertheless, the material is able to separate, for example, ethylene from ethane. And these molecules are quite a bit larger than the size of this window. So you can see here the equilibrium adsorption isotherms predicted in agreement with experimental measurements. But during diffusion, what happens is that if you look on the histogram of distribution, the histogram of window size for the empty structure, it is this one, blue. But when ethylene diffuses through and ethylene goes through the transition state through these 8-member ring windows, the structure expands by about 1 angstrom. This is a very large expansion. And this is not typical for zeolites. This is a very, very extreme example. Something like that would be much more common for ZIF materials or other metal organic frameworks, which are more flexible. And this example will be shown, I will show you later. So this, let's talk about diffusion in metal organic frameworks and zeolitic imidazolate frameworks. So for those who are not familiar with zeolitic imidazolate frameworks, these materials are a subset of MOFs, and they are composed of metal nodes and organic linkers. And why they called zeolitic imidazolate frameworks? Because they resemble topologies of many zeolites. This is ZIF-8, which is a prototypical example, and the nominal crystallographic pore size is 3.4 angstrom. Yet it can absorb many hydrocarbon molecules, and not only linear hydrocarbons, it actually can absorb xylenes molecules, which are way bigger than the size of the window. So clearly the explanation for such behavior should lie in the flexibility. But Is it always important to you to account for this flexibility? Actually, for predicting adsorption properties, it's quite surprisingly that you don't need to. For instance, for this ZIF-8, which has a rather large cage, if you use classical molecular simulations with the rigid structure and appropriate force field, you can actually predict adsorption of simple molecules pretty well, in very good agreement with experiments, and these examples for CO2 and CO2, methane, nitrogen, and even for some light hydrocarbons, you have very decent agreement. For diffusion, however, it's more complicated. So here is the experimentally measured diffusivity. This is from Ryan Lively, Bill Koras groups, the diffusivities of different hydrocarbons in ZIF. And as you can see, the range of molecules which readily diffuse, the size of those molecules exceed the size of the window by about at least 1 angstrom. So if you perform molecular dynamics, this is ab initio molecular dynamics simulations, you can again plot the histogram of the window size distribution just for the empty structure. And as you can see that this distribution has substantial tail. And this tail tells you that at least sometime the structure is substantially open for diffusion of other molecules. And as you can see, there is a frequency at which these vibrations occur. But as I mentioned before, another factor is the coupling between the molecular flexibility of the framework and molecular diffusion. And this coupling is shown very nicely here. This is work of David Scholl group, where they simulated diffusion of the range of molecules in ZIF-8, and they used the transition states theory. And as you can see, when the molecule is diffusing through the transition state, these are the histograms of the window sizes in these transition states. As you can see how they expand the window temporarily, but this expansion is very substantial and bigger than for zeolite. Another important phenomena which occurs in metal organic frameworks is the phase transition. So how can we understand this? So if you look on the free energy landscape of, say, a porous structure along some structural coordinate, if you have a rigid framework, it's going to have just one, say, energy minima, in which case the structure will be vibrating around some equilibrium position. It could happen that the structure can have several minima. For instance, this is a bistable structure, and in which case it can exist either as one structure or as a different structure. And if there's this free energy barrier is sufficiently high, it's not easy for the structure to jump from one state to the other unless there is some stimulus due to adsorption or temperature or pressure. Another situation is the free energy barrier is very low, in which case the structure can potentially explore many local minima and be really, really flexible. So ZIFs are, depending on which ZIF you look at, they are mostly corresponds to the left two situation. It's either one minima structure, or it's a bistable structure, or maybe tri-stable, and so on. And everything is determined by the free energy. So if you look on the Gibbs free energy, it has the internal energy term, it has the pressure term, and it has the entropy term, which favors entropically at specifically at high temperature. Entropy term becomes very important, and I'll show some of the examples. So the typical example is ZIF-7. So ZIF-7, it has structure which is somewhat similar to ZIF-8, except it has a bulkier benzimidazole linker, but it shows very different adsorption behavior from the typical Langmuir isotherm. It shows so-called type 5 isotherm with a prominent step, like no adsorption until certain pressure, and then sudden transition. And usually on desorption, this transition is associated with hysteresis. And what is interesting, some molecules can open the structure, like CO2, and some molecules cannot open the structure, at least in this range of pressures. So what happens here is actually a transition between the so-called narrow pore phase and the large pore phase of the material. You can try to rationalize what's going on by using so-called osmotic ensemble method pioneered by Couder and co-workers. If you look on the osmotic thermodynamic potential of the system, which includes the free energy of the solid, pressure term, and the ground potential related to adsorbed molecules. So in this case, what you can do by applying osmotic ensemble method, you can look on the adsorption isotherms on the materials which exhibit step like this and fit adsorption in individual structures, like a narrow pore structure or large pore structure, using this method, and you can calculate the free energy difference between the, say, large pore and narrow pore structures. And when you do that, you can see that this free energy difference actually has a temperature dependence, and at a certain temperature, particularly for ZIF-7, it is predicted that at a certain high temperature is actually going to transition from a narrow pore to the large pore structure. And this is what has been observed indeed in the experiments. So if you put this material in XRD cell and you start, say, let's say in vacuum, you start at room temperature material in this narrow pore phase. And as you heat it up at high temperature, it actually transitions to the large symmetrical, this hexagonal pore phase. And this is another look at this where you can do the heating and it transitions to the large pore phase, but then upon cooling, it actually reverses back to the narrow pore phase. So it is an equilibrium transition. And similar transition happens in the presence of gases. So for CO2, material at 30 degrees C is already in the large pore phase because CO2 is adsorbed. Then you start heating it up, CO2 desorbs and material reverts back to the narrow pore phase, but then upon further heating, it reverses back to the large pore phase. So it's a reversible transition. How can we rationalize this transition? So you can do molecular simulations, and I'm not going to focus on details, but they are in the cited papers. We had a reasonably good force field, which describes flexibility of ZIF-7. And what we did, we performed molecular simulations, which essentially mimic this XRD experiment by starting at a low temperature and then gradually heating the material up and performing molecular dynamics at each temperature in interval. And then we're using an isotropic unit cell, which allows for the variations of the volume. And if you do that, you can watch how the material transitions from the narrow pore phase into the large pore phase. And this is you watching the density, which decreases. So this is an example of entropically driven phase transition, because in this case, the entropy of the large pore phase is actually bigger than the entropy of the narrow pore phase. And we calculated these entropies using harmonic approximations. So first, we calculated the vibrational density of states from molecular dynamic simulations for narrow and large pore phases. And then we calculated the entropy difference. And indeed, the entropy difference for the large pore and narrow pore phase is positive. And what you can do next, you can plot the free energy. So the free energy in this case will be decreasing function because the T delta S term increases with temperature. And the free energy term decreases, and indeed, shows the transition from narrow pore phase to the large pore phase. And you can look on this free energy calculated versus free energy which we measured in experiment. There is a very good agreement, really good agreement. So this is, both for the magnitude of the energy difference at zero temperature, as well as the transition temperature. So it's about 700 K in experiment and about 600 K in simulations. We call it the method by which you heat the material gradually. We call it a snapshot method, and it's actually useful to try to test whether or not the material has a large pore phase. So what we did this is for ZIF-4. ZIF-4 is the very interesting and complicated ZIF. It has a smallest possible just the imidazole linker, but the structure is very flexible. And when we did these simulations with using this snapshot method and the temperature ramp, temperature ramp method. When we use this temperature ramp method on ZIF-4, we started with the low temperature structure. Then there is a transition to so-called high temperature structure. And this in agreement with experiments. Experiments are dashed lines. But then upon further heating of the material to unphysically high temperatures, but we can do it in computer simulations, we observed further expansion, and we called it expanded phase. And we were a little bit skeptical initially about the existence of this expanded phase until we actually found the experiments, and the experiments were done by Silvestre Albero at University of Alicante. And it turns out that nitrogen adsorption, if you measure nitrogen adsorption, material starts at 77K, material starts with a narrow pore structure, nothing gets absorbed, and then it jumps to the structure with pore volume, which corresponds to this predicted expanded phase. And then upon desorption, material shrinks again, and this corresponds to this well-known structure of the material in which it exists actually at room temperature, so-called ZIF-4HT. So there is a strong indication that this expanded structure does exist, and in simulation, it has been stabilized by entropy. In experiments, it has been stabilized by adsorbing nitrogen molecules. Let me go back to ZIF-7. If you look close on ZIF-7 isotherms, it's actually, they are more complicated. They have two steps. So they have one step, particularly if you measure at low temperature. This is like CO2 at 195K, 200K. It has one step, and then it has a second step, which almost doubles the capacity. And this is the same, this is the view in a logarithmic scale. So what you can see is you can try to feed these isotherms, which we did here with double Langmuir isotherms, and these feeds help you to understand what's going on, because you can see there is a nice Langmuir feed of the isotherms at low pressures, which corresponds to the narrow pore phase. And then there is a decent feed of double Langmuir isotherms at higher pressures. And what you can do also, you can plot the pressures of this transition as a function of temperature using Clapeyron equation. And you can see the first step, all these points line up on the Clapeyron equation. You can calculate the enthalpy of the process associated with this transition. You can also plot pressures corresponding to the second step, and you can see this is a different transition. And you can calculate the enthalpy of this transition. So this type of analysis is very useful when you have isotherms with steps. You can also do molecular simulations with individual isotherms with rigid structures, but you can look on molecular configurations at different loadings. And it turns out that if you take ZIF-7 large pore structure, you can simulate adsorption corresponding to almost double the experimental capacity. So in other words, you can simulate adsorption corresponding to this first plateau. And then you can simulate adsorption corresponding to this second plateau. So which is telling you that whatever transition occurs in this second step does not change the structure dramatically. It's a rather subtle, small rearrangement within the structure. And this is the enthalpies as predicted from molecular simulation in a rigid large pore structure of ZIF-7 in comparison with the enthalpies we obtained just by fitting the double length isotherms. So as you can see, this material has two types of sites, if you wish. It has high energy and a lower energy sites. And you can do the calorimetry. So we did a simultaneous adsorption microcalorimetry experiment in which we measured the enthalpy of this process. And these are the measured enthalpies corresponding to this adsorption of CO2 at different temperatures. And as you can see, it's about 28 or something kilojoule per mole. However, if we overlay the enthalpies predicted from molecular simulations just for the rigid structure, there is a difference, especially in the range of this first step. And this difference is due to the enthalpy of transition. So this difference corresponds to the enthalpy difference due to the transition of ZIF from narrow to large pore phase, which is endothermic process, which consumes some heat generated by CO2 adsorption. And if you actually integrate these differential enthalpies into the cumulative enthalpies, integral enthalpies, you get the difference in enthalpy between narrow and large pore, which is in agreement with other calculations and molecular simulations. So I will stop here to answer some questions, and then in the last part of the talk, we will delve into calorimetry and heat source adsorption.
All right, so we do have a couple of questions so far. Let's start with, you mentioned, you were talking about surface barriers at the beginning of the talk. From a molecular simulation perspective, are there reasons why something like a surface barrier might not follow Darkin's relationship?
I'm a little bit so I'm going to say the surface. I don't see the reason why the surface barrier should follow Darkin relations. I think we're talking about somewhat different things, right? So the Darkin relations is usually the relation between the collective diffusivity and the transport diffusivity. It's an assumption that you can go from collective diffusivity to you can replace the collective diffusivity with the self diffusivity and then use thermodynamic correction factor to calculate transport diffusivity. So when we include the surface barrier, we're including some additional phenomena, in my opinion. So we're including something which is relates to the different transport resistance. So
Okay, so just to clarify then, so for something like an internal micropore diffusivity, it's meant more so for that instead of a surface barrier diffusivity. And
that's right.
Okay.
That's right.
Great. So then just a follow up to that, in general, how well does Darkin's relation actually correlate like measured internal diffusivities in the micropore? Is it more like a rule, or is it a hard law?
It's a loaded question. I'm going to say that it is system specific, and for certain systems, it has been verified that it works really, really well. But for certain, but again, it's system specific.
Okay, and then we'll just do one more quick question. How does the temperature affect the flexibility of zeolite frameworks?
It's a very good question. Quite obviously, the magnitude of the flexibility increases when you increase the temperature. I showed the plot for DDR zeolite when you compare, say, 300K and 600K. The difference is smaller than one might think, because probably the structures are very sufficiently, stiff. Zeolites are sufficiently stiff structures, so they still, retain largely similar degree of flexibility, but definitely it increases with temperature.
Great, and actually, we just got a question in Zoom as well that I'll ask you before moving on. This is from Danuka Gabala. Do you think that it's the same mechanism for ZIF-8, two-step isotherms for nitrogen and CO? I guess, do you think that it's the same mechanism for ZIF-8 for the two-step isotherms of nitrogen and carbon monoxide?
The nitrogen at low temperature induces the structural change in ZIF-8. So it's not a very substantial change, but it has been measured. I actually do not recall the CO isotherm and how would it look like. So I cannot answer this question. I just
maybe they might have been talking about carbon dioxide.
Is it carbon dioxide or carbon monoxide?
In the question, it's written as carbon monoxide, but it might have been a typo.
Yeah, sorry.
That's okay. So from there, if you would like a follow-up or a clarification of that question, just retype the question. And in the meantime, Dr. Ravikovitch, I'll have you present the next part of your talk.
All right. So in the last part, we will talk about the heats of adsorption. As I mentioned, it's a very, very important quantity. It's a partial molar enthalpy difference between gas and adsorbed phases. It's actually one of the most important parameters in the heat balance and design of adsorption processes. So what are the ways to assess the heats of adsorption to calculate? So the typical way of doing it is to use a Clapeyron-Clausius equation, when you use the set of isotherms and then you use this rigorous relation. This is using fugacity to calculate the isosteric heat of adsorption, which is a negative of the enthalpy of adsorption by convention. You can also measure it in a differential adsorption calorimetry of Tyan-Calvet type. And what is important is that for physical adsorption, which we typically deal with the porous materials, and for typical porous materials, this heat of adsorption is a weak function of temperature. So let me illustrate this. So this is CO2 on 13x zeolite. Isotherms very carefully measured within the range of ambient and a little higher than ambient temperatures. If you use the Clapeyron-Clausius equation and you plot the so-called isostairs of adsorption, and you can try to do regression on those points, it is very typical to have 3, if not 4 nines. So they are really linear. And if you do not see 3 nines or 2 nines, you should start worrying about the quality of your experimental data. So this is a fact which has been shown many times. This is example. For example, this is a much wider temperature range. This is from Martin Bülow, who developed isosteric method to calculate the heats of adsorption. And so these are really linear isostairs in a different systems, different molecules. In the calorimetry, what we do in the calorimetry, we do a simultaneous adsorption and microcalorimetry experiment when we measure adsorption isotherm, but with dosing into the calorimetric cell. And in the calorimetric cell, in the Tyan-Calvet type microcalorimeter, you have 2 cells, one with the sample, another one without sample. and you're measuring, and these cells have an array of thermocouples, and you're measuring directly the heat of adsorption. So it's a direct measurement. So when we do it on CO2 on 13X, we compare here 3 different results. One is our calorimetry. Another one is the Clapeyron-Clausius. I just showed you analysis of adsorption isotherms and calculation of the heat of adsorption by derivative of the adsorption isotherms. And we compare with the literature, with the paper by Alan Myers and Martin Bulow and collaborator. We have, I'm going to say, perfect agreement. So this is why so there is a very nice agreement. Now, are there any other ways to calculate the heat of adsorption? In certain situations, you can use one temperature to calculate heat of adsorption, but at the condition that you have a perfect adsorption model. So this is an example of a quench solid DFT, classical DFT model, which predicts rather well adsorption on mesoporous materials such as like MCM41. In this case, what you can do, you can measure one isotherm, you can fit this one isotherm using the pore size distribution, using the kernel of theoretical adsorption isotherms, and you can fit this isotherm. Then you can use predictions from the DFT at a different temperature, slightly different temperature, and predict the experimental isotherm at a different temperature. And then you can use Clapeyron-Clausius to calculate the heats of adsorption. And if you do that, it actually gives you really nice agreement with the experiments. Again, this implies that you have a perfect model which is totally predictive from one temperature to the other. This is generally not the case. And in molecular simulations, what we do typically in molecular simulations, one uses so-called fluctuation formula to calculate the heats of adsorption. I think I list here a number of classical references how this formula is derived, and this is the end result. So it relates the fluctuations in the energies and a number of molecules adsorbed in the grand canonical ensemble, and relates it to the isosteric heat of adsorption. So when we saw this, we were very much surprised. So this is the 4A zeolite, and this is CO2 adsorption on 4A zeolite. On the left, you see experimentally measured isotherms and simulated isotherms. There is a very good agreement. Not perfect like for siliceous zeolites, but not bad at all, really good. And on the right, you see simulations of the heat of adsorption and experiments. So simulations at 3 temperatures, experiments at 2 temperatures. And what you see immediately, that there is a strong temperature dependence. So at 300 K, then at 450, and then 600 K, there is a quite substantial temperature dependence of the heat of adsorption. And this dependence is confirmed experimentally. This is why we this is not what you would expect, because I just showed you example of 13X zeolite, where in a sufficiently wide range of temperatures, the heats of adsorption were temperature independent and the isosters were perfectly linear. So we did very extensive checking that was done with, we did very extensive checking. What we did simulations in a closer range of temperatures and used Clapeyron-Clausius to confirm the results from the fluctuation formula. As you can see, there is some scatter because molecular simulations, they have some scatter. So if you try to differentiate isotherms using Clapeyron-Clausius, you're going to get some scatter. But in general, there is a nice confirmation of the results. Similarly, at a higher temperature and even higher temperature. Again, so full consistency between the fluctuation formula and the Clapeyron-Clausius. different routes to get to the heat of adsorption. This is another experiment. We took another cationic zeolite, and we did the calorimetric experiment. And in this case, it's even more prominent. So you can see calorimetry at 300, 400, 440, and 500 K. There is a clear temperature dependence. So to double check this, we did independently calculations of the Henry constants. So we fitted the Henry constants of the measured adsorption isotherms, now just adsorption experiment. And as you plot the logarithm of the Henry constant as a function of inverse temperature, you are not getting exactly a straight line. And if you calculate the heats of adsorption from just adjacent temperatures, you actually see quite substantial, very substantial temperature dependence, which is in agreement with the calorimetric measurements. Again, so experimentally, we check that we have consistency between the calorimetric and adsorption measures. We started looking in the literature, and yeah, sure enough, Richard Baer reported temperature dependence for polar molecules adsorption in cationic zeolite, particularly in lithium X zeolite. At very low temperature, though, that was observed at something like around 200 K. So what's going on? So molecular simulations give you a way to look at what's going on. What you can do, you can plot the histogram of interaction energies at different temperature. And you can clearly see that the interaction energies decrease as you increase the temperature. Average. You can also plot the interaction energies for different sites. You can identify within these LTA type zeolites, you can identify three types of sites. You can identify so-called dual cation site when CO2 actually interacts with two cations. You can also, and this is the highest energy. You can also identify so-called single cation sites when the CO2 interacts with one cation. And also you can identify just a CO2 which is adsorbed somewhere in the middle of the cage, which has the lowest interaction energy. So what's going on? It turns out that if you plot the histograms of each individual site as a function of temperature, you find that there is a shift. So in other words, at the lower temperatures, the population of the strongly interacting dual and single cation sites is higher than at higher temperature. So the molecules at as our temperature increases, the molecules move from these strongly interacting sites and interact less strongly with the zeolite. So this gives rise to the difference in the temperature, in the heat of adsorption. So what about siliceous zeolites? So we looked on typical siliceous zeolite. For example, if you look CO2 in MFI zeolite, nothing changes with temperature. That's why the heat of adsorption is independent from temperature. However, if you look on some of the siliceous 8-membrane zeolites, something like ITQ29, which is siliceous LTA, you start seeing very substantial change in the heat of adsorption, especially as you decrease the temperature. And it's very dramatic, especially for ITQ29. It is from 18 kilojoule per mole to 30. That's a really huge change. So what's going on here? Yeah, these are more detailed simulations for CO2 in siliceous LTA. Now we consider as a function of loading and at different temperatures. And you can see at higher loadings, the heats are pretty much temperature independent, but in low loadings, there is a very substantial temperature dependence. Again, if you take this rather interesting non-monotonic curve at around 195 K, again, we did very careful simulations and we checked by Clapeyron clauses that this is indeed the case. So experimentally, we have nice agreement between predictions, between experiment and predictions. And what simulations show that ITQ29 has two types of sites. And you have window sites, and CO2 adsorbs at low loadings in these window sites. And then there is a rest. So there is a redistribution of molecules between the window sites and the rest of the sites within the LTA cage of ITQ29, which gives rise to this redistribution. And this redistribution gives rise to the temperature dependence of heat cell adsorption. Methane, nitrogen, they show rather weak temperature dependence, something which is much more commonly observed in the literature. So this is my summary. So we talked about the small pore zeolites for kinetic separations. I demonstrated that zeolites are flexible, and this is a very interesting area to focus on. I showed some novel methods for modeling diffusion and flexible frameworks, and generally flexible frameworks a very interesting area. Novel flexible frameworks, so they're called zeolitic imidazolate frameworks, they are much more flexible than zeolites, and also it is much more common to see phase transitions within materials of this type. And the problem is to predict the occurrence of these transitions and at what conditions they occur, and how you just go from, X-ray structure reported for a particular MOF at particular conditions to a more general understanding of the behavior of the material in the range of precious temperatures and adsorbed molecules. The last topic which I covered was the heats of adsorption. So we were quite surprised to demonstrate that actually there is a significant temperature dependence of the heats of adsorption, even for well-known zeolites. We expect that this temperature dependence will be more prominent for materials where we have more distinct adsorption sites, for example, MOFs. And so the caution is that if you use Clapeyron-Clausius equation, you should use it in as narrow range of temperatures as possible to be able to do the accurate calculations of the heat of adsorption. So with that, I'll give you some suggested readings. So for diffusion and generally, especially zeolites, of course, the book is by Jörg Cargill, Doug Ruthven, and Dorothy Theodoro, Diffusion and Nanoporous Materials. These two volumes is a must-have. Now, Jörg is editing a topical collection for adsorption journal called Diffusion and Nanoporous Materials, and some papers already appeared online, and other papers will be published, during the rest of this year and next year. And this is a very comprehensive collection from experimental point of view and also from modeling point of view, deep look on different techniques, and I highly recommend. On metal organic frameworks, I honestly myself was a little bit lost because there's so much on metal organic frameworks. I can recommend the book by David Farusing, but also you should look on many recent reviews on the topic, and they are updated. There is so much there. On the heats of adsorption, the classical papers are by Alan Myers, and I mentioned these papers, so these are accurate treatments. And for molecular simulations, there are two classical books by Alan Tildesley, Frankel Smith on methodology of molecular simulations. Also, I recommend a book by David Scholl on quantum density functional theory. And I also strongly recommend webinars by Randy Snur and also by Lev Sarkisov and Miguel George, and they cover fundamentals of molecular simulations of adsorption. So with that, I would like to conclude, but I'm going to give acknowledgement. So obviously, many people were involved in some of the results which I presented today. I specifically would like to acknowledge these people and from ExxonMobil and collaborators from different organizations, and also support of ExxonMobil for this fundamental research. Thank you very much.
Thank you, Peter. So we have a couple more questions for you. We'll start with one from YouTube. This is from David Madden. Can you perform similar calculations using the virial method as opposed to Clausius-Clapeyron?
Yeah, I expected this question. Yes, you can do that. If you can feed the whole isotherm, of course you can use it. In general, the Clapeyron-Clausius, I find that if you can feed the isotherm with some analytical form, then obviously the numerical differentiation becomes much easier.
Okay, we actually have a follow-up to the question that was given before. So this is from Danuka Gabala again. They say, thank you for taking my question. Yes, I was talking about carbon monoxide in our experiments. We have seen similar steps to carbon monoxide like the nitrogen isotherms.
Yeah, so I'm not familiar with this. I cannot recall exact experiment that is referred in the question, but I can see that something similar might happening if you especially if thermodynamic state of carbon monoxide is similar to nitrogen. I would expect, and the molecules are reasonably sized similarly. So I would totally expect that this step can also be occurring due to the carbon monoxide adsorption.
And for the material, they're talking about ZIF-8.
Yes, yeah, I understand, yeah.
Okay, so another one that we have from YouTube. This is from James Burrow. They ask, if you fit Langmuir models to various temperature isotherms, constant saturation capacity, affinity is the only factor that changes, would you think that Arrhenius analysis of affinity is accurate for heat of adsorption?
Very good question. I actually had a slide on that. If I can, I don't know if I show this slide or not, but it's actually, this is a good example. This is a double Langmuir. And you need to remember that in Langmuir, by definition, it's one side, right? So each Langmuir is one side. So the heat is independent of temperature from the beginning. So if you have something like two-side adsorbent, and you can, adsorption is represented by double Langmuir models. You have perfectly linear isostere of adsorption. But there is no room in this model to have a temperature dependence of the heat of adsorption. It's just not here. So, right? So in order to have the temperature dependence, you need to have not only different adsorption sites, you need to have a redistribution of molecules between these two sites occurring when you change temperature. Does that answer the question?
I think so. So we have two more questions currently in. This is another one from YouTube. It's from Maria Elizalde. Can you mention an effect which would be indicative of a phase transition in ZIFs?
Mention effect?
Yep, I'll just read the question again. Can you mention an effect which would be indicative of a phase transition in ZIFs?
Manifestation of, well, if you have a phase transition, you have, these are crystalline materials, so you will see, you will see the difference in the structure. So if you can afford to do the experiment with the monitoring, say, X-ray diffraction, for example, you will see the changes. And that's another indication of phase transition often is the step on the isotherm. It doesn't necessarily mean that you have a phase transition, but more often than not, for the microporous materials, if you have adsorption and you have a sharp step on the adsorption isotherm, you should suspect that something similar to transition occurring. These are good indications of a possible phase transition.
Great. And we have one more from Zoom right now. This is from Andreas Seidel-Morgenstern. Thanks a lot, Peter. The heats of adsorption are measured and or analyzed theoretically, typically for a single component adsorption. Does this information allow the prediction, a proper prediction of the heats of adsorption released during, if we have an adsorptive mixture?
Well, if you know individual heats of adsorption and you can assume certain adsorption theory, you can predict mixture behavior. So to the extent that you predict mixture behavior, you can estimate the mixture heats of adsorption.
There's a follow-up to that as well. There's probably also some nonlinearity involved.
I don't think I understand the question. What do you mean?
I think it might be a comment. So I think he's just saying that there might also be some nonlinearity involved. And so there's superposition. There seems to be one other question or a comment. This is from David Donacci. Danuka, maybe you have already seen this paper, but it might be worth helping your carbon monoxide question. Unfortunately, I'm not sure if I can show this link, but I can post it in the YouTube video afterwards. And it's to a paper. Okay, we have a couple more questions actually from YouTube as well. So this one is from Bhubesh. He's actually a colleague in my group. Does the temperature dependence of isosteric heat of adsorption offer any significant process advantages?
Very good question. It's process specific. So some processes are dominated by different things. So it really depends on particular process configurations, and it may or may not be significant depending on your particular heat balance of your process.
Okay, and we just got a question also from Stefano Brandani. What is the predicted behavior for binary diffusion coefficients when one molecule modifies the mean opening of the window?
It's a good question. I don't think we did, and I'm not honestly aware of simulations which would demonstrate the behavior, this type of behavior. What I would assume that if the time which molecule spends in the transition state is short enough, then basically the binary behavior will be sufficiently independent. In other words, one molecule passes through the narrow window, and then another one is essentially on its own. So this is actually a typical example in the state member ring zeolites. It's actually, they are decoupled systems. So the binary mixture is essentially there is no much cross correlation occurring. I think what might be happening if the molecule somehow allows, if two molecules allow to go hypothetically through the same transition state. I'm not aware of systems like that. So I would still assume that in general, probably it's still one molecule at a time for the typical barrier.
Okay, and I think this might be a follow-up to that as well. So the flexibility in general, how does this change as a function of gas mixtures? Is the flexibility a phenomenon or just a function of the fugacities of the single gases?
I don't quite understand what does it mean flexibility is phenomena. So definitely in a mixture, if you have different components in a mixture, they will interact differently with with the adsorbent, and they will change the. So if you look on this osmotic framework, for example, you can see that they will change the ground potential component corresponding to the overall osmotic potential of the system, and it will change at which, say, pressure this mixture will undergo a transition, for example. So the mixture adds complexity from the point of view of that you have many molecules, but it does not fundamentally change the flexibility. So it changes the, if you wish, the stimulus which material, experiences, and which influences what state the whole system will be.
Okay, I think that's actually it for questions right now. So I will hand off the host to Dan, and he'll show the rest of the slides.
Dan, I believe you're muted.
Thank you, Peter. We'd like to thank all of our attendees for joining us today and for asking questions for Peter, helping to illuminate the topics that he's looking at today. The next IAS webinar is tentatively scheduled for Friday, December 4th at 9:30 a.m. New York time. You can see the time zone conversions on the slide here. Our speaker will be Professor Handan Tezel from the University of Ottawa, and she'll be presenting on binary adsorption isotherms, and especially in how to calculate and measure those isotherms using pulse chromatography. And Nick, I'd like you to have an opportunity to announce your Twitter poster conference.
Thanks, Dan. So we're also happy to announce the first IAS Twitter poster conference. This aims to elevate the research of graduate students and early career researchers through a free poster conference. This will be hosted on Twitter between the 7th and 11th of December. If you'd like more information about registration and how to set up your posters and so on, we've included a link at the bottom of the screen that will have the rest of that information.
All right, with that, we'd like to thank everyone for joining us today. And we look forward to seeing you again in December. And with that, we say good day. Thank you.